All right, so I'm going to start right at the top of your packet, which is lessons 1 through 5. Did everyone bring this back with them today? Okay, you guys are great. I appreciate that. So what we're going to do today are lessons 1 and 2. There's a lot of reading involved in these and some chart making, so I think that's sufficient. We'll save 3 for next week. We have no need to rush whatsoever. You guys are in great shape, and we're even going to review. So on here, today's date is the 20th. So we're going to do this lesson today. And then we're going to do this today as well. And your test for independence is what we'll conclude with today. And that's, again, another heavily regions topic that tends to come up all the time. So that's super important. Next week, we'll do your general probability rules. What's next Monday's date? 26th, right? So we'll go 26 and 27. I'm sorry, 26 and 26. And then we'll do your review and then quiz. If I give you a quiz, it'll probably just be something I don't say anyways. So this will be review on the 27th. All right, and then after that, we're getting into May. And then shortly after that, end of the school year in June. So probability, what's important with these today is actually the notation that I write out is required. Do any of you think that you might pursue like our AP stats course in the future in the building? Maybe possibly. Stats is great for anyone that's going into like medicine or if you're going into like poli-sci or business. So with the statistics, we do emphasize your notation. And typically when you get into a college level stats course too, all your explanations have to be written in complete sentences. Now for our purpose here, sometimes I will, sometimes I won't, just because I know sometimes it gets difficult to be able to check when there's so much detail involved. But notational things tonight, please don't leave off in the little parts where you have to show your work too. So I'm going to start nice and easy right at the top here. And again, we have a ton of reading to do. So grab your highlighter and just be ready with all this vocabulary. Does anyone in here love to read out loud? Nobody? Yeah, I figured that was coming. I figured I would ask. So I'll do my best here. And I'll start right at the top. So we're going to look at events here that are random. Your basic probability terminology in your box here. You have what's called an experiment, which is just some sort of procedure that you're going to use. Sometimes it involves flipping a coin or spinning a spinner. Outcome is your result. An event is a collection of all your outcomes, and the sample space is where you list them. So you can list them just out, like in a big list, or you can do what's called a tree diagram, which I'm sure you've probably seen in the past. So number 1 gives you an experiment is run whereby a spinner is spun around a circle with 5 equal sectors that have been marked off it as shown. What is the experiment? What would I say, guys? What's the experiment here? Yeah, just spinning the spinner. Yep. So my experiment is spinning the spinner. I'm spinning the spinner. Then you are asked, what is one outcome of the experiment? So we'll pick a number. Which one do you like? 3. So I'm going to say landing on a 3. Landing on 3. Nice, simple, and easy so far. Next, what is the probability of spinning the spinner and landing on an odd number? So this is where I'm going to introduce some notation. And again, this is meant to prepare you for any stats course you take down the road. So what I do is I say probability of getting an odd. And again, I would really like to see you use that notation too. So how many odd numbers do I have up here? Yep, and out of how many total outcomes? There we go. So 3 out of 5. And then again, as a decimal, that would just be equal to 0.6. So what is the event here? So the event here would be spinning an odd. So your events would be spinning and landing on an odd. So spinning and landing on odd. And then what outcomes fall into the event? So outcomes, you're just gonna list these. So outcomes are 1, 3, and 5. Okay. Again, nice, simple, easy so far. So probability, that's how we're gonna write these. We're gonna get our favorable outcome over our total is what that means. So based on the above definition, what two numbers is probability always in between? You guys know? No, you've done some probability in the past. If an event is impossible and it won't occur, what's the probability? Here. Yep. And then what's the probability it is certain to occur? 100. Yep. So probability as a decimal always must be between 0 and 1. So as a decimal, it is always between 0 and 1. So always between 0 and 1. 0 being impossible to occur, and 100% would be obviously likely to occur, certain to occur. So 0 and 1. All right, so next we're going to sketch out a tree diagram. So a fair coin is flipped 3 times and the result is noted each time. Your sample space consists of ordered triples, which would represent head on the first toss, head on the second, and a tail on the third. So draw a tree diagram to show all the different outcomes in your sample space. So if I flip a coin, the first thing that I can obtain, I'm going to do this over here so I have a little bit of room, is I can obtain a heads or I can obtain a tails. So that's flip number 1. Now I'm going to keep going to flip number 2. So from flip number 2, I could also get a heads and a tails. Yep. Same deal. Heads and a tails. That's my second flip. Now I'm going to do it one more time. So off of this one, I can get a heads and a tails. Off my next flip, I can get a heads and a tails. And off my next flip, same deal, heads and tails. And then lastly, heads and tails. All right, how many total outcomes? What do we got? Looks like 8, right? So 8 outcomes altogether. Now I apologize because your questions are actually on the back. So I'll do this. You flip and I will read you the questions so you don't have to go back and forth, and I'll leave that up here. So you can just look right at the tree diagram so you don't have to do the flipping. So the first question asks, what is the probability of getting all heads? So I'm going to look on my tree here. And to get all heads, it looks like how many times? So this is 1 time. Are there any more? Nope. So for part A, or I for that matter, you're going to say 1/8. So 1/8. And 1/8 as a decimal is what? 0.125? Yep, so equals 0.125. I'll do this. I'll go back and forth for you. So this was 1/8, equivalently 0.125. All right, next one, probability of obtaining exactly 2 heads. I'm going to do this one in blue, light blue, so I can circle it for you. 2 heads. I see 1. I see 2. I see 3. Is that it? Yes, it is. Yep, so 3 out of 8 is my next answer. And 3 out of 8 is equal to what as a decimal? Thank you, that's what I thought, 0.375. All right, and now I'll go orange on this last one. All heads or all tails? How many choices do we have here? All heads, we already took care of that one. That one's my pink one. I'll go over this one again. All tails. How many choices, guys? Yep, just 2. So this one is equivalent to 2 over 8. And then as a decimal represented as, you got it. Good. All right, so number 4. A survey was done by a marketing company to determine which of 3 sodas was preferred by people in a blind taste test. Results are shown below. So the first term that's up here, and again, I know you have some exposure in the past to some probability. It says empirical probability. That is like based on experimental data. Okay, so when you see that, this is based on experimental data. Like if you polled people. So find the empirical probability that a person selected at random from this group would prefer soda A. So again, we want to emphasize notation. So I'm going to say the probability that they prefer soda B. So you're just basically using the parentheses to basically disclose what you're finding the probability of. So just some sort of little explanation there. So soda B is how many? 24 out of how many total? 53. And can we grab a decimal for this? 0.453. Thank you. 453. And that was out of 53. Perfect. All right, next, we are going to find the probability instead that a person selected at random would not prefer A. Well, if they don't prefer A, what do they prefer instead? B or C? Yep. So I'm going to write this as the probability that they prefer soda, B or C. And what you're going to do is add those together. And again, I know it seems strange, but we do typically require you to show that. So you're going to show 24 plus 11 divided by 53. All right, so this is equal to 35 over 53. And does somebody have this decimal? Wait, which is it?
I was reading the wrong one.
Oh, it's okay. 0.660, thank you. 0.660. Thank you. Awesome. All right, what do we think? Pretty easy so far? Good. So the next table below is what we refer to as a two-way table. What this does is it analyzes 2 categorical variables. So essentially 2 different categories. The categories we are looking at down below are going to be gender and whether or not the town should build a new high school. So essentially an opinion. Your gender is what we call a row variable, and the opinion is the column variable. But when you go to draw one of these and set it up, no, it doesn't matter which one you technically put where. Total column is established right along the margin of the table. Therefore, we refer to that as a marginal distribution. Okay? So marginal distribution just means it's located right along the margin of my table. Are we good with all the terminology? This is called a two-way table. It describes 2 categorical variables. So again, that just means 2 categories of information. And then you always put totals on these. So when you get to homework questions, if totals are missing, my advice is always add them in. Row variable is your gender, and then column variable was our opinion. All right, I think your questions carry to the back. Yep, over here. So the school board of Waldo enrolled funded by taxes. They decided to interview eligible voters to determine if the school should build a new high school facility to replace the current high school building. There's only one high school in every town, and every registered voter was interviewed. So that's good. You do want things like that included in your test. The data from the interviews is summarized below. So based on this survey, we want to back this up with math. Do you think the school board should recommend building a new high school? Well, what should we look at, guys, from the table? Yep. How many said yes, and if it represents a majority? Excellent. So I'm going to look at the probability that the person surveyed said yes, we should do a new high school. And how many total yeses do we have? Yes, we have 273 out of a total of 515 surveyed voters. And does this reflect a majority? Yeah, what was it equal to? 0.530. Perfect, thank you. Which for this part, I mean, it might be helpful to think of it as a percent. So this would be 53%, and that is a majority, so yes. So we're going to say yes. Since majority said yes, or you can say 53% said yes, as long as you back it up with some math. The majority said yes.
So for questions like that,
Mhm.
are they solo because like that's not a broad margin there, so you have nothing on it.
Yes, you base it on the data. Yep, absolutely. We will get to analyzing whether data is, like good or not, for lack of better words, and your margin of error later on in your unit. Yep, you're just like 20 lessons ahead. So letter B, a male is selected at random. What is the probability that he would indicate that the town should build a new high school? All right, we do this in orange. So we want males. So male selected at random. How many total males do we have? Yep. And then I'm going to show you how to write this too. And then we want the probability that they should build a new high school. So that I'm going to circle which number? Good. So here's how we write this using proper probability notation. I want the probability of a yes vote given the condition that the student is male. And this helps set these up. So I do number of yeses, 119, divided by 241. And does anyone have that? 0.494, thank you. Perfect. All right, next, I'm going to switch colors again. And again, this is where your highlighters come in helpful too. Next in my table, I am going to go red now. A female selected at random. Okay, how many total females are we talking? Good, 274. And what is the probability that she would indicate if the town should not build a new high school? 114, right? Yeah. Right contained within my row. So here's how I'm going to write this. I want the probability of a no vote provided the condition that she is female. And this rule is summarized for you down below too, written in proper notation, but this is where I'm getting that from. So we're going to go 114 over 274. Anyone have this decimal? 0.416. Thank you. Okay, so that's the formula that I've been kind of working you through, is this right here. That is called conditional probability, and it is dependent on a particular condition. These cases, the condition was gender. Okay, but that's the formal notation of what you're doing here. This means and. You guys seen that before? Yeah, I was going to say, sometimes middle school you've seen that, sometimes you haven't. There's also a symbol for or as well. But that's your conditional probability formula. So it's the condition that she said no, given the fact So health officials in Milwaukee, Wisconsin are concerned about teenagers with asthma. People with asthma often have difficulty with normal breathing, and in a local study, researchers collected data about the incidence of asthma among students enrolled in the high school. All right, flip over to the next page. Lots of reading. All right, so students in the high school completed a survey that was used to begin this research. Based on the survey, the probability that a randomly selected student at the high school has asthma is 0.193. So right now, the condition we're looking at is asthma. So I'm going to start, and we're going to be making a two-way table. Again, this is not the only way that this can get done. There's many options, but the first condition I just heard was asthma. So I am going to look at asthma, and then I'm also going to look at students that don't have asthma. And then it's always advisable that you add on a total column and row. All right, so I'm going to start this. So that is what we call our first categorical variable. So your category is asthma. And now I'm going to read this, and I'm going to find another category to compare. And we'll fill in the numbers in a second. So hold that thought on the numbers. Next, students were asked if they have someone in their family that smokes. So again, you can set this up many different ways. So I'll go no smokers, and then I'm going to go at least one smoker. Again, order doesn't matter. I was just trying to keep everybody the same. No smokers, at least one. And of course, on the very end of this, I'm going to add total. And then we're going to start filling in your numbers here. So you're just going to do some basic math with just addition and subtraction. Way easier than logs. So probability of a randomly selected student having at least one member in the household who smokes was reported to be 0.421, and the probability that one household member smokes and has asthma is 0.120. So there are many ways that you can do these. So all these decimals would add up to 1.0 right here. What we also sometimes do with these decimals is we get rid of them and we create what is called a hypothetical 1,000 table. Why 1,000? How many places would I have to move this to clear it? 3. So that's what I'm going to suggest here. But again, it would work the same way if you just use decimals. They just get cumbersome to write. So I'm going to put a 1,000 here, just to clear the decimals. Now I'm going to start labeling some things. So we know the probability of a randomly selected student at this high school having asthma. So my total asthma sufferers are 193. Now, before you go any further, can't you find this number? Yeah, so what's 1,000 minus 193? This is 807. Save you the word. Okay, now I keep going through my table. Next, probability of a randomly selected student having at least one member in their household who smokes is 421. So what else can we find? Can't I go right to the left of that now? 1,000 minus 421 is beautiful. So build it as you go. I think we have one more in here somewhere. Yeah, you kind of need it. And the probability that a randomly selected student has at least one member who smokes and has asthma. That's right here. That is 120. Which means now we can fill in the rest of the table. So on the left, I have 73. And next one here, I would have 506 if I subtract. And then in the middle, my last one comes back is 301. How's that so far? Pretty good? Okay, now you're going to answer some questions based on this. Based on your completed two-way table, estimate the probabilities of a fraction and a decimal to 3 places. A randomly selected student has asthma. How many total kids are we talking here? 193, yep. Now, of that row, what is the probability that the student has at least one household member who smokes? So I say the probability of at least one smoker given the condition that you have asthma. So this is the number we divide by. So I'm up in this row, I'm going to circle this one in yellow, at least. So I'm going to go 120 over 193. 120 over 193, and that is equal to 0.622. What do you think? Is that a pretty big chance there? 62%? Yeah, I'd say so. All right, so letter B. Next, we are looking at, do this one in blue. A randomly selected student does not have asthma. What's my new total? 807. Sorry, it keeps messing up like that. What is the probability that he or she has at least one household member who smokes? So I'm going to use that number, 301. So I'm going to write out my probability statement again. So probability of a smoker given no asthma this time. And you can abbreviate things too. And this was equal to 300 and what was that number? 301. 301 divided by 807. So I'll have to scroll that on you. And that comes back as 0.373. All right, next. So letter C. A randomly selected student has at least one household member who smokes. What is the probability that this student has asthma? So we want at least one household member who smokes. So what's that total? I'll go orange on this one. At least one smoker is 421. What was our condition? Has asthma, right? I'm going to reuse this number again. So this is a column instead. Obviously, we're going up and down. So I'm going to go 120 over 421 in a second. So I want probability of asthma given the condition of there is at least one smoker. And that was equal to, the numbers were, I just circled 120 and 421. And then you're going to divide it up. All right, I got points. Like 285. Yep, just like that. And this one we kind of already discussed. Do you think whether or not a student had asthma was related to whether or not they lived with someone who smoked? 62.2% were yes. So let's say yes. 62.2% had asthma living with a smoker. You know, something like that. But again, when you do these reasons and justifications, you're looking to back it up with the math. All right, how's that one? Pretty good? Mm-hmm. Yeah, we usually use decimals. Yeah, I mean, you could do both too if you wanted to, but typically we just look at the decimals. Yep. All right, guys, over to the next page. You're going to flip over all 4 of these. When you come in tomorrow, this is your first assignment. It is rather long. All right, all the way over here. So what we're going to get at with your second lesson today is what we refer to as a test for independence. which is basically just a rule that you kind of have to remember. And you're going to set it up in a two-way table here as well. So this is formally your rule. You do your general probability and you compare it to your conditional. So we'll kind of walk through 2 or 3 examples of that today, and then we'll do more with it again next week. So when I said, oops, I apologize. Not crazy on me. So your first example here, just to kind of work you through this, say you throw a coin, the probability of getting a heads is 0.5. If you throw the coin a second time, the probability of getting another heads is 0.5. Do those events have anything to do with each other? They do not. Therefore, we call them independent. From a probability aspect, what you're going to be looking for is you're going to want, when we go to write these rules out, equal probabilities. So when you compare your 2 events and you set them up, you're going to want these to be equal to each other. So here's a counter example. So suppose you were dealt a card from a deck of 52. Probability of getting a red is 50%, so half. And then if you get a red card on the first card that you're dealt, you are now left with only 25. So the probability that you draw a second card that is red is now reduced. Now it's 25 over 51. So these events are not independent. Okay? So I'm going to have you fill in this chart. This is the chart you're going to see for homework as well. So you can kind of use this to help you. So let me give you some numbers all the way across. This is going to refer to your first categorical variable is gender, and your second is whether or not the student participates in an after-school athletic program. So I am giving you these numbers. You don't need to produce them from anywhere. So we are going to go 232. I'm going to go right across 348 and total 580. This is a hypothetical 1,000 table again. So this total was 1,000, meaning the males were 420. So you did not survey an equal distribution of male and female. This number is going to be 168. And I'm just giving you this data. This is 400. Making this the 600, and my last one would be 252. Okay, so you're going to answer a couple questions with this table, and it does, go on to the back here as well. Sorry, got to do some flipping with probability. There's a lot of text involved. It says, for each of the following, indicate whether or not it is a conditional probability, and then calculate. So we are looking for the probability that a randomly selected student. That phrase means this is out of the grand total. And that randomly selected student does not participate in after-school athletics. All right, how many non-participators do we have? 600. Good. So I'm going to do this number over this number here. So I want the probability of no after school. This is not a conditional. This is out of the grand total. You did not apply male or female to it. So I just use 600 over 1,000. So the answer to this is no. This is not conditional because it is not based on gender. This one's just out of the whole total. Conditional is usually really specific, so keep that in mind. So obviously this is just 0.60. All right, tell me this one, guys. Is this one conditional? Yes, good. The probability that a selected student who is female, so this is now only out of females, does not participate in the after-school athletic program. So now my total is just 580, and of the 580, I only look in the row, and that was 348 must be, right? Yep, so I know I have that covered. So now I'm going to say the probability that we don't participate again, so no after school, provided the condition of gender in which she must be female. All right, so we have 348 divided by 580. Anyone have this decimal yet? Oh, you guys are fast. Say it again. Thank you. 0.6. So actually, the gender matter here? It appears not. Those are equal. Oh, I'm sorry. So bless you. The probability that a randomly selected student who is male does not participate. So is this one going to be conditional as well? Yes. So this one is also a yes conditional because you are applying the condition of gender. So yes conditional. It is gender specific. And let's calculate it. Gender specific. So I'm going to write it first and then I'll flip. You guys don't need to. So probability of no after school given the condition that they are male. So no after school given that they are males. All right, I'm going to grab those two numbers again, but I'll flip for you guys. No after school and males. All right, what do we got? No after school and males. What number over what number here? 252 over 420. 252 over 420. All right, that decimal came back as, yep, 0.60. Thank you. So would your prediction of whether or not a student participates change if you knew the gender? Wasn't this the same as the girls? Yeah, so you're gonna say no. So no. Males and females both 60%. Well, males and females were equal probabilities. So equal probabilities. Okay. So what we're going to begin is what we refer to as a test for independence. Okay? You don't need to read any of that. I will summarize it for you. So to set up a test for independence, what you're going to be looking at is whether or not your two probabilities are equal. So we always start and we do just the general probability and then we compare it to the conditional. So we're going to have to kind of flip back and forth. I apologize. So based on your definition of independence, and again, this means the same thing as if a question tells you to do a test for independence. So it means the same thing as that. Independence. And what we're going to be looking for is our probability of A has to be equal to our probability of A given D. So that is the rule per se. Now here's how I like to do this. I like to circle them right in the table. So to start, based on my test for independence, are the events. Number one, randomly selected student is female. Stop. So I'm going to do the probability of being female. I'm going to go back to my table and I'm going to circle this in pink because I want to show you a pattern that makes this really easy to do. So I'm going to go back and I'm going to circle probability of being female. All right, what do we got here? Probability of being female is? Female? I was going to say, I'm saying 580.
Oh,
That's okay. I was just making sure we were looking at the same thing. Out of how many? Yep. Can you guys please circle those? Especially for this part, because it makes it really, really helpful. So now I'm going to scroll down again. Sorry for the scrolling. And I'm going to go 580 over 1,000. And this is equal to 0.58. Okay, now I'm going to read the second part because you'll notice I ignored it initially. Now what I want to test is that the student is female and participates in the after-school program. Now I'm going to go orange. So the probability that she is female, because I always start with the same thing I ended with here, given the condition that she participates. I'm going to abbreviate too. Here is the easiest way to do this. It's going to follow the same pattern that I started with. Do you guys see how I went this one, this one? It's going to be the same pattern. So she participates. So what column, first or second? I know you can't white out the highlighter, can you? So this column. So what number over what number do you think? You got it. Not a coincidence. That's always how they work. They follow the same pattern. So 232 over 400. All right. Can someone get that answer, please? Is it? Over 400. Yep. So are these independent events? Are the probabilities equal, guys? Third strike, right, Josh? It's okay. Yes, these are independent because they were equal. I'm abbreviating. Okay, that's the test for independence. All right, and then two more, and then that's it for now. So number 4 says 80% of dogs in a local kennel are in good health. I'm going to translate that. So probability of the dogs being in good health is 0.8. 0.80. If the events that the randomly selected dog at the kennel is in good health and weighs more than 30 pounds are independent, underline, highlight, something. So now it told me the probability that the dogs are in good health and they are over 30 pounds, yes. Over 30 pounds. And it didn't tell us what it was, but it told us that these are independent. Then what do you know this probability must be? Exactly, 0.80. Yep. Why? Because these have to be equal. So independence, test for independence means these have to be equal. Okay. And then this last question down below is just how to represent these symbolically. So choice 1, multiplying them together, this is true. This also is another test for independence that does work. We're going to talk about this next week. So this is true. Next here, this is the rule that you actually just tested for, right? Yep, that's what we just got right here. And now look at choice 2. If I divide them, do I get 1? Yeah, 0.8 divided by 0.8 is 1. So this is true. This is true, but again, I'm going to give you more of that next week. So I know you don't have any way to determine that yet. So the only one is wrong is choice 4 because they are flipped. So that is the only statement that is not necessarily true. All right, how do we feel with probability so far? Okay, so do this and star these pages for me. So then tomorrow, I don't have to put into your time and you know exactly what you were doing. So go forward first. You're going to put a big star on problem set 2. Is there a front and a back? It probably is. Front and back. Is there another 2? No. So star on those 2 pages and go back to problem set 1. And you will notice how many pages is it? It is 4. Why? Because a lot of these are really fast, okay? So this is page. So please make sure you flip. Okay. So tomorrow when you come in, you've got your review on logs that's on Delta, your quiz on logs that's on Delta, or you have these two assignments as well. These two assignments, I will check Monday when you return to class. Delta stuff is due Friday afternoon. Okay? We feel comfortable on those so far? All right. You've got like 5 or so minutes to organize yourself.